After understanding the terminology which is necessary for the coordination compound, we must understand the IUPAC nomenclature. Afterwards, what are the theories which are also developed for the coordination compound to explain. You have to remove the 2 electron which is there in the stable electronic configuration. So now totally there are 26 electrons will be there in the nickel. So how do you all write that? Coordination compounds can form 2 types of complexes. One is homoleptic complexes, other one is heteroleptic complexes. Hello my dear students, a warm welcome you all. Myself is Purnima, lecturer in Department of Chemistry at Vidhyaashram Pre-University College, Temple of Excellence, Mysuru. My dear students, in our last class, we have discussed about the revision class for the Unit 8. Today, we are going to start with a revision for the Unit 9, Coordination Compound. So, what we are going to understand in this unit, it is very important. As I said, each unit will have their own weightage, and in the coordination compound, you have to learn some of the basic terminology such as central metal atom, ligands, what does mean by coordination number, the types of coordination complexes, and you also learn about IUPAC nomenclature of coordination compound. Okay, and their theory in bondings of Werner theory, valence bond theory, and lastly we have crystal field theory. Okay, these are the important topic that I have covered in my concept class. Okay, remember? So here I have placed an example to understand a few terminology which is very much necessary to understand this unit. The first terminology is central metal atoms or ion. You can see that in this complexes, the central metal atoms use your cobalt, which has been surrounded by 6 types of ligand or 6 ligands, correct? 3 are the amine ligand and other 3 are chlorido ligand. And also you can see that we have placed a square bracket to indicate the central metal atom as well as the ligand. Okay, that square bracket which we call it as what? Coordination sphere. And the charges also we have mentioned at the top of this coordination sphere, which is nothing but charge of the complex. Clear? Then the central metal atom along with the ligand, the charges, sometime without the charges, we will write the elements outside of this coordination sphere. I can write this structure as CO, NH3, 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 Cl, Cl and Cl. Okay, and this Cl, okay, and this nitrogen we can write in this way also, CO, NH3, Cl3. Okay, these Cl3, okay, there are 3 chlorido ligands are nothing but counter ion. Why we will write that counter ion? To balance the central metal atom. And how to find out the oxidation number of the central metal atom also I have explained in the concept class. There are 2 ways will be there. One is for the anionic complexes, what is the formula, and for the cationic complexes, what is the formula that we have to follow. So everything will be there in the concept class. Please go and watch for the concept class. Now I'll go with a weightage of this unit. As we have known that from this unit there will be a no 1 mark question, there will be a no 2 mark question. But remember, we can expect the 3 mark question, and it can be split into 2 plus 1 or 1 plus 1 plus 1, and most of this 3 mark question, it is based upon the theories and the complex writing. Okay, we'll discuss directly with the 3 mark question which has been repeatedly asked from the coordination compound. The first question is, mention 3 postulates of Werner theory of coordination compound. As I said, after understanding the terminology which is necessary for the coordination compound, we must understand the IUPAC nomenclature. Afterwards, what are the theories which are also developed for the coordination compound to explain? The first theory is the Werner theory. Later on we use a VBT, that is the valence bond theory. Afterwards, finally we are using the crystal field splitting theory. Correct? So, what is Werner theory and who is a Werner and what are the postulate was given by the Werner? It is also very important. Okay? Alfred Werner was a scientist. He has prepared the different kinds of coordination compound and he observed the physical and chemical properties of those compounds. And finally, he come to the conclusion that by saying that the coordination compound will have, there are two types of valency. Okay, he said that every coordination compound consists of two types of valency. One is primary valency and the one is secondary valency. Okay, and he says that the primary valency, it is nothing but your coordination number. Okay, primary valency, it is nothing but coordination number, and secondary valency, it is nothing but the number of coordination bonds. Okay, I'll go with this example, that is CONH3 6 times. Okay, and Cl3. Okay, in this example, you can see that there are 6 ligands are ligating towards a central metal atom. So, their coordination bonds will become how much? 6. But how to calculate the coordination number for the cobalt? It is different. As I said, we will consider this as X and there are ligands will be there 6 ligand into the coordination number of this ligand plus counter ion how many? 3. And what is the oxidation number for the chlorine? It is -1. So, totally we will get X is equal to +3. This is the oxidation number and this is nothing your primary valency. And number of ligands which are ligating towards the central metal atom, they are nothing but a coordination bond which is nothing but your secondary valency. Okay. And later he said that primary valency are ionizable and it is always balanced by negative ion or the negative charges. Whereas secondary valency are stable and it is non-ionizable and it cannot be balanced by negative charge, but usually it is balanced by ligands. Okay, usually it is balanced by ligand. That is why if you see that this complex, when you dissolve it in water, what does it forms? If you dissolve this complex in water, it forms CONH3 6 times plus Cl3 minus ion or 3Cl minus ion. Okay. So, this reaction indicates that the primary valency are balanced by negative charges and it is ionizable. Whereas the secondary valency, I know that secondary valency are formed by the ligands only. It is always balanced by the ligands only and if you dissolve it in water, this will not be ionizable. It will be remain as such. Okay, this indicates that the secondary valency are non-ionizable and it cannot be balanced by negative charge. It is balanced by ligands only. Okay, and they said that primary valency is non-directional, whereas secondary valency is directional because the secondary valency which tells about what is the geometry of the complex. So, by knowing that how many ligands are coordinating towards a central metal atom, we can easily tell that how many coordination bonds are there and what is a complex are formed. By looking at the ligands only, you can tell that there are 6 coordination bonds can be possible with the amine ligand, so that the complex will be octahedral like that. Okay. This was a postulate was given by Werner. Next question. On the basis of valence bond theory, account for the hybridization and geometry and the magnetic properties of tetracyanidonickelate or tetracyanidonickle complex ion. And also they have given the atomic number for the Z, atomic number for the nickel is 28. So, for writing this VBT structure for the given complex, remember, first of all, you must know that what is the atomic number for the central metal atom. So, here the central metal atom is your nickel and the atomic number for the nickel is 28. Okay. And you must know that how to write the stable electronic configuration, and before that you have to calculate the oxidation number for the nickel. Okay, so how do you all calculate this? So I'll take the nickel as X plus how many cyanide ligand? 4. 4 into minus 1 is equal to minus 2 because this is a charge. So X minus 4 is equal to minus 2, X is equal to plus 2, which means that nickel will be present in plus 2 oxidation state. So you have to remove the 2 electron which is there in the stable electronic configuration. So now totally there are 26 electrons will be there in the nickel. So how do you all write that? The excited electronic configuration of the nickel in plus 2 oxidation state, that is argon 3D8 and 4 is 0. So here I have written 4 is 2. Why? This is a ground state electronic configuration. So in the excited state, the 2 electron from the 4s will be get removed out. Okay. So the electronic configuration will become argon 3D8, 4s0. That is why I have split the 3D. So you can count that 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons are there and 4s is 0. And we know that the nickel is get attracted towards a cyanide. Cyanide is the strongest ligand. Because of the attack of the strongest ligand, cyanide because of the attack of the strongest ligand, the unpaired electrons which is found in the nickel, they get paired up. When they get paired up, the electronic configuration in the 3D orbital will be looks like this. But it has to attack by the other 4 cyanide ligand. For the 4 cyanide ligand, we must have a 4 vacant orbital. Correct? So that is why we are taking the 1 orbitals of the 3D and 1 orbitals of the 4s and 2 p orbitals of the p orbital. 2 p orbitals we are taking. So what will be the hybridization now? So there are only 1 d and 1 s and 2 p. So hybridization will become dsp2. Okay. So the hybridization of tetracyanide ion is dsp2. If dsp2 hybridization is there, obviously it follows the tetrahedral geometry. Since it is tetrahedral, we must know their magnetic behavior. So here you can see that there is no unpaired electrons after the hybridization of ligands with a central metal atom. So since there is no unpaired electron, they are diamagnetic in nature, and you can see that, as I said, there are 4 ligands will be there and there are 2 possibilities will be there. One is tetrahedral and the one is square planar. So the geometry of the complex for the dsp2 hybridization is square planar geometry. Okay. So this is how each and every point you have to write for the 3 marks. Next. Using the valence bond theory, explain the geometry and hybridization and magnetic behavior of COF6 3-, given that atomic number for the CO is 27. Now here also you must calculate the oxidation number for the cobalt. I'll take it as X plus 6 into minus 1 is equal to minus 3. X minus 6 is equal to minus 3. X is equal to plus 3. Clear? And I have written the ground state electronic configuration of cobalt. As I said, it exhibits in the plus 3 oxidation state. Now I have to remove 2 electron from the 4s and 1 electron from the 3d. So the electronic configuration will become 3d, 6, 4s, 0. Now count how many electrons have filled now. 1, 2, 3, 4, 5, 6. Okay. So this is a 3d orbital and 4s and 4p. Now I know that the halogens are very weak. They are electronegative. They are not a strong ligand. So that this unpaired electron will be least as such, but we want 6 vacant atomic orbital for the hybridization. That is why I will take 4s, 4p and 4d. So from the 4s I will take 1 orbital and 3 p orbitals I will take, and 2 more orbital I want I will take from the 4d. So hybridization will become 1s, 3p and d2. So it is sp3 d2 hybridization will be there, and you can see that there are 4 unpaired electrons will be there. Since there are 4 unpaired electrons, they are paramagnetic in nature, and also you can see that there are 6 ligands will be there. If the ligands are 6, And also, if the hybridization is sp3d2, definitely the complex will be octahedral. Okay. Next, on the basis of valence bond theory, explain NiCl4 2 minus. Okay. So, same thing here as I explained with the nickel with the cyanido ligand, here we have chlorido as the ligand. Okay. So, we have chlorido ligands here. So, atomic number for the nickel is 28. So, excitation of the nickel from the 0 to +2 is possible. So, we have to remove the 2 electron from the 4s. So, totally there are 8 electrons will be there in 3D. I know that halogens are very weak and they are electronegative. The electron pairing will not at all takes place against the Hund's rule. It will be leaves as such. But I want the 4 atomic orbital, vacant atomic orbital I want. That is why I will take. So, 1 s and 3 p orbital I will take. So, the hybridization will become sp3. If the sp3 hybridization is there, and you can see that there are 2 unpaired electrons are there, and they are paramagnetic, and definitely since there are 4 ligands are there, you know, they are tetrahedral in nature for the sp3 hybridization. Okay. Next, draw the energy level diagram for the splitting of d orbitals in an octahedral crystal field theory. So, you must know that when I say it is octahedral complexes, how does the splitting of or how does a degeneracy in the d orbital must takes place? Okay. So, as we all know that the d orbital consists of 5 atomic orbital and it can be written as dx square minus y square, dz square, dxy, dxz and dyz. And we know that these d orbital, okay, due to the approach of the ligand, they get excited and split into 2 energy level. So, that energy level can be called as T2G and EG in case of octahedral complex. In case of tetrahedral complex, these energy levels are also different. Okay. So, in EG level, we have dz square and dx square minus y square, and in T2G level, we have dxy, dyz and dxz. Okay, xz we have. Between these two, you know, we can call the center as barycenter. And you can see that how even though it is d orbital, when they split, you know, it shows a different energy level. So, for the exam, you must know that which complex they have asked and how this d orbital will be split and give rise to the energy level. You must have this idea to show that how does the octahedral splitting will occurs in the d orbitals of octahedral complex. What are homoleptic complexes? Give an example. My dear students, from this unit, as I said, there can be a direct 3 mark question or 2 plus 1 mark also. Okay. So, in the 1 mark, they can give you any of the complexes to name for the nomenclature, and in the 2 mark, they can definitely ask with the types of complexes which are formed by coordination compound. Usually, coordination compounds can form 2 types of complexes. One is homoleptic complexes, other one is heteroleptic complexes. So, we must know that what are homoleptic complexes. If the coordination compounds which are formed by only one type of ligand, which means that the central metal atom, if it is surrounded by only one kind of ligating atom, such types of complexes which are formed by only one type of ligand are said to be homoleptic complexes. Here, homo stands for the same. If the same kind of ligand which are ligating towards a central metal atom and forms the complexes are said to be homoleptic complexes. So, I can give you the example of cobalt, which has been surrounded by 6 type of amino ligand, NH3, 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 then NH3, then NH3. Okay, the total charge of this complex is +3. Okay, so you can see that this is a central metal atom surrounded by 6 same type of ligands which are ligating towards the central metal atom. Hence, it is known as what? Homoleptic complexes. Next, we have heteroleptic complexes. What are heteroleptic complexes? Give an example. Here, hetero stands for different. If the different ligating ligands, if it is ligating towards the central metal atom, then we say it is heteroleptic complexes. So I can go with the cobalt only, which has been surrounded by 4 amino ligand and 3 chlorido ligand. 4 amino ligand and 3 chlorido ligand. Then such complexes are called as what? Heteroleptic complexes, and the charge of this complex is +1. Okay, you can see that there are 2 different types of ligands are there. One is amino ligand and one is chlorido ligand. Okay, this is all about the types of coordination complexes. So this is all about the types of question, that is mainly 3-mark question, which has been repeatedly asked from this unit. Hope you all understood with the unit. I'll come back with the next unit. Till that, take care and be safe. Thank you.